Derivatives are an extraordinarily powerful math tool typically taught through finding tangents by looking at how a line might intersect a function at two increasingly close points. The limit is usually taken to find the equation for the derivative, but what if we just didn't do that? What if we did derivatives differently? Alright, hear me out. Let's use the same concept of getting really close to a tangent, but instead of moving points closer together, let's start with a line and move it until it becomes the tangent. Let's try it on something simple like y equals x squared. This is probably the easiest example possible, but let's just run with it. So we have our supposed tangent line y equals ax plus b, and the goal is to express b in terms of a such that the line is tangent to the parabola, and then we want to find the tangent point. So let's just find the intersection points by setting them equal to each other, and we get the equation x squared equals ax plus b, which becomes x squared minus ax minus b equals 0. A simple quadratic equation where we just need to pick a and b such that there's only one point of intersection. And to find out what we want b to be, we just complete the square. We end up wanting this to be x minus 1 half a squared, so b would be negative 1/4 a squared. And the intersection point would be when x is equal to 1 half a. Voila! We now know how to find the derivative of y equals x squared in a most definitely incorrect way by starting with the slope, adjusting it to a tangent, and then finding where it intersects. If we apply this to the point p squared, a is equal to 2p and b is equal to negative p squared, so we get the line y equals 2px minus p squared. This checks out with other methods of finding derivatives. I mentioned earlier that this was a best case scenario, so let's see what happens when we instead have y equals x cubed. Well, it's a slight pain. X cubed equals ax plus b is not a good equation to have, and our line likely intersects twice, once at our supposed tangent, but also somewhere else on the graph. Thankfully, it's still possible using a few tricks. In general, a cubic will have three solutions that will factor into some form of x minus r1, x minus r2, x minus r3. Fortunately, at least two of them will have to be the same at our tangent, so our polynomial doesn't just pass right through to make an intersection. So now we have x minus r1 squared, x minus r2. Expanding this equation or using Vieta's can give another trick. If you don't know Vieta's, just look at the x squared coefficient. It's 2r1 plus r2. More generally, Vieta's tells us that the coefficient for the second term is always the sum of the roots. It doesn't stop there though. Vieta's can also give us the next term by using the roots. In our case, it would be r1 squared plus 2r1r2. More generally, it would just be the sum of all pairs of roots. And now we move on to the final term, which is simply and easily just the product of the roots, which in our case gives r1 squared r2. Now we can go on to the next trick. We know that the coefficient for x squared is 0. This gives us the direct relation between r1 and r2. r2 is 2 times negative r1. Conveniently enough, r1 also happens to be the x value where our tangent-ish line intersects our cubic. I'll leave it as r1 for now as we continue. Now we can substitute r2 in all of our equations to get our derivative. The coefficient of x would be negative a, and before we had r1 squared plus 2r1r2. After substitution, we get negative 3r1 squared, so a would equal 3r1 squared. The last term, or negative b, which we found earlier to be r1 squared r2, is now negative 2r1 cubed. B is sadly very unimportant because a is actually our derivative. The slope of the tangent line on y equals x cubed would in fact be 3x squared, the actual derivative. This took a lot of effort to get something rather simple, and I can't say it gets any easier. You can try the same old tricks for a quartic, but it simply starts to fumble. Kind of like how there's a quadratic formula which is easy, a cubic formula that isn't nice but exists, but no formula for a quartic. I won't say it's impossible, but you're better off trying something else. A final test for this method would be looking at some other function, like the exponential function e to the x. We set it equal to our line ax plus b, and now we give up. This equation is simply awful to solve, unless we get really cheeky. Set a equal ex and b to e to the x times 1 minus x so that the right side is simply e to the x. And in practice here, it looks like this cheesy strategy actually tells us the derivative of e to the x is e to the x, an answer other methods would agree with. But okay, it isn't nearly that simple. Otherwise, why wouldn't the derivative for x squared just be a equals x to get x squared equals x squared? If we set a equals x and b equals 0 to get x squared equals x squared, when x becomes fixed to some variable like p, the line intersects the parabola at p squared, but also 0, 0. That's the problem here. Setting something equal to itself doesn't confirm that there's only one point of intersection. Unfortunately though, I'm out of gimmicks here today. I hope you never try to do derivatives wrong and learn the right ways of doing math. But maybe you don't care and want to have a little fun sometimes, or you want to stretch stupidity as far as you can go. In that case, I'll be right here to do more wrong until I'm right.